Okay, so today I'm going to talk about self-supervised learning. This video is based on a talk by Andrew Zisserman. I rendered this talk at IIIT, and most of the content is copied from his slides. This has most of the information at a high level and is just an introduction to some of the ideas. So what is self-supervision? Uh, it is a form of unsupervised learning where the data provides the supervision. These definitions will make more sense later when we look at the examples. And in one of the examples, we are given a grayscale image and we try and predict the RGB color image. So we are withholding the color information and then trying to predict it. So in general, we withhold some part of the data and task the network with predicting it. The task defines a proxy loss, and then the network is forced to learn what we really care about. Okay, so in real-time user-guided image colorization with learn deep priors. In this example, our training data is just color images, and the output is a colorization of the image and a sort of semantic segmentation. Semantic segmentation just means that we know what object every pixel in the image corresponds to. Any image can be broken up into its grayscale and color components, and in this manner can serve as a free supervisory signal for training the network. So here we are using the CIE LAB color space instead of RGB, but the idea is same. The L channel sort of represents the lightness or intensity of the color, and the A and B represents the actual color. So here we have a grayscale image, and we are trying to predict a color image of a fish. Here, by learning how to colorize the fish image, the network has learned that a fish is usually brighter than its surroundings, and the surroundings are often green in color. It has learned the separation of fish and background without having the training data specifically label it as such. Okay, so now let's look at this example in detail uh, of the real-time user-guided image colorization. In this case, after the network has learned how to colorize an image, it colors the trees as green and elephant as gray. In this paper, the authors simulated thousands of user inputs while training the network. For example, the training sample for the colorization took the gray value in an elephant and set it as a user input. The authors then created an interface which allows the user to define the color at a specific point. And here we are trying and defining this point as pink on the head of the elephant, and let's see what happens. Okay, so the network learns to color the elephant pink, which means it has learned a semantic segmentation without the labeled training data, which is super cool. Okay, so now let's take a look at our next example. Self-supervised learning of a facial attribute embedding from video. Here the input is just videos of people talking, and the output is an embedding that can be used for predictions of various different facial attributes like facial key point detection, emotion recognition, and also head pose estimation. Here we see all the different tasks which the embeddings can help, that is head pose, expression, and facial landmarks. So let us see how this network is defined. So this is called a FABNet or facial attribute network. And the input here is a source frame from the video and a target frame which is separated from a few frames from the source frame. The network generates an embedding for both of them and then concatenates them. This is then used to generate a warp image which maps each pixel on the source frame to a pixel in the target frame. So the idea is that you can generate the target frame from the source frame, and the loss is computed by comparing this generated frame with the original target frame. So here you can see that just videos of people talking are used to generate the training data. To generate the target frame, the network needs to identify a mapping of the pixels. The embeddings need to encode the positional information in some way, as the eye colors need to match the eye in the target frame. Therefore, the network learns embeddings that are useful. So here we can see that the embeddings generated by FabNet also lead to a very low prediction error on popular facial landmark datasets. So to better understand what the network learns, let us look at the nearest neighbors in the embedding space for a query image. In here you can see that the faces returned with a low distance to the query image have a very similar pose and emotion, and that sort of helps us understand what the network is actually learning, and we can clearly see that it has captured things like emotion and pose in the way the embeddings are generated. Okay, so our next paper is tracking emerges by colorizing videos. Here, the training data is just videos of human doing different actions, and the output is video colorization, tracking, and even skeletal tracking. So let's exactly see how the tracking information is generated. Okay, so here we are given a color video, and the task is to colorize all frames of a grayscale version of a video using the reference color frame. So here the network tries to sort of map which pixel in the reference color frame maps to which pixel in the frame in the grayscale video. It does this for every frame, and what this allows you to do is that because you have correspondences for every frame, you have a set of correspondence across multiple frames. So the tracking just emerges for free as you colorize all the frames. For example, here, if you color the car pixel as red in all the frames, you're effectively tracking the car as you know where the red points are in all the frames. Therefore, this allows you to learn tracking without any training data, which is really cool. So here there are some other interesting examples that we can see. Here only the skeletal points were marked, and we can see that it does skeletal tracking. And here we can see the results of trying to colorize a grayscale video using a reference color frame at the bottom. Okay, so the next paper we are going to talk about is objects that sound. Here, the training data is just videos of humans playing different instruments, and the output is a network which has the audio and images in a common embedding space. And by that, what you can do is you can say you can show a picture of a guitar and you can get all the sounds that the data set has related to a guitar. And so it is sort of similar to a Siamese network, which is used for face recognition, but it has two different modalities. Okay, so let's see how we train this network. This is done using audio-visual co-supervision. We know that regular videos are semantically consistent and synchronized. So you have a video of someone playing the drums and you have a video of someone playing the guitar, and you know the sound of drums corresponds to someone playing the drums, and you know the sound of guitar corresponds to someone actually playing the guitar. Here we using these videos of people playing drums, guitars, or different instruments. We generate positive training examples by saying we know an audio corresponding to someone playing the guitar corresponds to an image of someone playing the guitar. Here we know the audio clip of someone playing the drums is associated with an image of someone playing the drums, and the sound of a drum does not correspond to the image of someone playing a guitar, and that's how we generate negative training samples for our network. So let's see how this network is trained. So the network has a visual subnetwork which generates an embedding for the image, and an audio subnetwork that generates an embedding for the audio clip. The visual subnetwork has an image of someone playing the instrument as input, whereas for audio, a short audio clip is converted to an image based on its frequency and then sent to the audio subnetwork as input. The embeddings are both generated in a common embedding space. The way it is trained is that if you have a picture of a guitar and audio for guitar, then the distance between them in the embedding space should be really low. And if the picture is of a guitar and the audio is of a drum, then the distance between them should be really high. Training the network in this way then allows both the audio and the image to be in the same embedding space. We can now see, now let's look at an example. Here we see that if we query with an image of a guitar, with an image of a guitar, we can query So here by querying a guitar image, we could retrieve all the audio clips with people playing a guitar. Okay, so now let's look at our last paper, the conversation, deep audio visual speech enhancement. So here, our training data is just videos of people talking, and the output is that we are able to isolate individual voices in videos, and we could also mute background noise in videos. So let's first understand what this means. Let's say there is a talk show where there are multiple people speaking. So you can just select who you want to listen to. Let's say you want to listen to the third person or you want to listen to the second person. You can just select which person you're interested in listening to. The way it works is that the network is able to separate a speaker's voice by using their lip movement as signal. So the lip movement can help understand who the speaker is and the content being spoken. So let's first take a look at an example to understand what is actually happening. So here there are 4 speakers, and some of them are speaking at the same time, and by just scrolling over them I will be able to choose which one I want to listen to.
Justification for Buran Wani. Allow me to complete. I'm
so this
no,
guy
I'm
is
not.
speaking,
You are.
and we can see that this guy is really quiet,
That is exactly what you are insinuating.
and we can listen to
If
her
I may
speaking.
add, building a case for. Why are you building a case?
Okay, so I hope you understood what this network allows you to do. So now let's see how it is trained. Okay, so this is trained by using synthetic audio data. And to train this, we need videos of people talking. So we have our original video and it has an audio component and a video component. So then we take the audio and then add interference to create a synthetic noisy audio. And the video is also an input to the network. The enhancement network then just tries to predict the original audio. So there's no label required for this. The training loss is just based on comparing the generated audio with the original true audio. Therefore, for training, you just need data of someone talking. And the network uses the lip movement in the video as signal and uses it to separate the true audio from the synthetic audio. Okay, that's all. I hope you enjoyed it and have a better understanding of what self-supervised learning allows you to do. All the links are in the description below. Thank you.